Welcome to Bot Thoughts by Soft. I'm Alex, and today we're tackling a problem every AI engineer hits eventually. You've got a 70 billion parameter model that's brilliant. It answers questions perfectly, writes beautiful code, understands nuance. There's just one problem. It needs 140 gigabytes of memory to run. Your GPU has 24. So what do? Throw money at cloud GPUs? Accept a worse model? Or get creative with math? Sam, walk us through the options.
This is one of the most practically important topics in AI right now. The gap between what's possible in a research lab with 8 A100 GPUs and what's deployable in the real world on affordable hardware is enormous. But it's shrinking fast, thanks to three key techniques: quantization, which makes models smaller; speculative decoding, which makes them faster; and optimized serving frameworks that squeeze every last drop of performance from your hardware. Let's start with quantization, because it's the foundation everything else builds on.
We wrote a beginner's guide to quantization in blog 27. What is it, and why does it work so well?
Quantization is reducing the numerical precision of a model's parameters. A standard model stores each parameter as a 16-bit floating point number. That's 2 bytes per parameter. So a 70 billion parameter model needs 140 billion bytes, or 140 gigabytes. Quantization says, what if we store each parameter with only 4 bits instead of 16? That's a 4 times reduction. The same 70 billion parameter model now fits in 35 gigabytes. That's 1 GPU instead of 4. The key insight is that neural networks are remarkably tolerant of reduced precision. Most of the information in those 16 bits is redundant. The first few bits capture the important signal, and the rest is noise. Studies consistently show that 4-bit quantized models retain 95 to 98% of the original model's quality. For most practical applications, you literally cannot tell the difference.
But there isn't just one way to do quantization. We compared 3 major formats in blog 28: GGUF, GPTQ, and AWQ. This is where people get confused. Which format should you actually use?
Each format is optimized for a different use case. GGUF is the format used by Llama, CPP, and Alama. It's designed for CPU and mixed CPU-GPU inference. If you're running models on a laptop or a machine without a powerful GPU, GGUF is your format. It supports flexible quantization levels from 2-bit to 8-bit, and it's by far the most user-friendly. Just download a GGUF file and point Alama at it. GPTQ is a GPU-optimized format. It uses a sophisticated calibration process that minimizes quality loss during quantization. It's the best choice when you have a dedicated GPU and want maximum quality at a given size. AWQ, Activation-Aware Weight Quantization, is the newest and often the best for production serving. It's faster than GPTQ at inference time because it's designed around how the model actually processes data during inference, not just how to compress the weights efficiently. My rule of thumb: GGUF for local and CPU, GPTQ for quality-critical GPU workloads, AWQ for production serving at scale.
Quantization makes models smaller. But what about making them faster? Speculative decoding is one of the coolest tricks in AI right now. We covered it in blog 29. How does it work?
Speculative decoding exploits a counterintuitive fact. Verifying a sequence of tokens is much cheaper than generating them. Here's how it works. You have 2 models: a large target model that gives high-quality responses, and a small draft model that generates tokens quickly but less accurately. The draft model generates a batch of, say, 8 tokens very fast. Then the large model verifies all 8 tokens in a single forward pass, which is much cheaper than generating 8 tokens sequentially. If the draft model guessed correctly, which it does about 70 to 80% of the time for straightforward text, you just got 8 tokens for the cost of 1 large model inference. If it guessed wrong, you accept the tokens up to the first mismatch and try again. The net effect is 2 to 3 times faster generation with 0 quality loss. The output is mathematically identical to what the large model would have produced on its own. You're not approximating. You're using the small model to skip ahead and the large model to verify.
Let's talk production serving. Once you've quantized your model and optimized inference, you need a serving framework to handle real traffic. We compared the big three in Blog 30: vLLM, TGI, and Triton. What's the landscape?
vLLM is the current darling of the open-source community. Its killer feature is page detention, which manages GPU memory like an operating system manages RAM. Instead of pre-allocating a fixed context window for every request, it allocates memory dynamically in pages. This means you can serve more concurrent users on the same hardware. In benchmarks, vLLM typically achieves 2 to 4 times higher throughput than naive implementations. TGI, text generation inference from Hugging Face, is the enterprise option. It integrates tightly with the Hugging Face ecosystem, supports all the major model architectures, and has production-grade features like request queuing, health checks, and metrics out of the box. NVIDIA Triton is the heavyweight for multi-model serving. If you're running multiple models, not just LLMs, but also embedding models, vision models, and custom models, Triton orchestrates them all on shared GPU resources. It's more complex to set up but unmatched in flexibility. For most teams starting out, I recommend vLLM. It's the easiest to deploy and has the best price-to-performance ratio.
Give us some real numbers. If I have a single A100 GPU, what kind of throughput and latency can I expect with these different configurations?
On a single A100 with 80 gigabytes, running Llama 3 70 billion at 4-bit quantization through vLLM, you can expect about 40 to 60 tokens per second per user with a batch size of 1. With concurrent batching of 32 requests, throughput jumps to about 800 to 1,000 tokens per second total. First token latency is typically 100 to 300 milliseconds. For a 13 billion parameter model, those numbers roughly triple. Speculative decoding on top adds another 2 to 3 times multiplier on per-user latency. Compare that to API pricing. Running your own A100 costs about $2 to $3 per hour on cloud providers. At those throughput numbers, self-hosting becomes cheaper than API calls once you're processing more than about 100,000 tokens per hour. For high-volume applications, the savings are enormous.
Now let's go to the other extreme. Instead of serving millions of users from the cloud, what about running AI on a phone or a Raspberry Pi? Edge AI is a whole different world. We covered it in Blog 31.
Edge AI is one of the most exciting frontiers. The idea is running models directly on the device, no internet connection needed. Privacy is total because no data ever leaves the device. Latency is near zero because there's no network round trip, and it works offline. The challenge is that phones and IoT devices have limited memory and compute. A modern flagship phone has 6 to 12 gigabytes of RAM and a neural processing unit that can do maybe 10 to 20 trillion operations per second. That's enough to run a 3 billion parameter model comfortably, or a 7 billion parameter model with aggressive quantization. Apple, Google, and Qualcomm are all pushing hard here. Apple's Core ML can run quantized models with hardware acceleration. Google's MediaPipe and ML Kit provide standardized APIs. And Qualcomm's AI Hub has pre-optimized models ready to deploy on Snapdragon chips. We're about 12 to 18 months from phones running capable AI assistants entirely locally.
So you've got cloud, local, and edge. Blog 32 was our deployment strategy guide. How do teams decide which approach to use?
It comes down to 4 factors. First, model size. If you need the largest, most capable models, you're in the cloud. 70 billion plus parameters require serious GPU infrastructure. Second, latency requirements. If you need sub-100 millisecond responses, edge deployment is the answer. No network round trip can compete with on-device inference. Third, privacy and compliance. If data can't leave the device or the premises, edge or local deployment is mandatory. Fourth, cost at scale. Self-hosting is cheaper above a certain volume threshold, but comes with operational complexity. Many teams use a hybrid approach. Edge for simple, latency-sensitive tasks like intent detection, local servers for moderate workloads, and cloud APIs for the most demanding queries. Route each request to the tier that makes sense for that specific task.
Let's close with predictions. Where is model optimization headed? What should developers be watching?
Three things. First, one-bit models. Research from Microsoft and others is showing that models can maintain surprising quality at extreme quantization levels. We're approaching the theoretical limit of how small a model can get while remaining useful. Second, dedicated AI chips. NPUs, neural processing units, are now standard in phones and laptops. Within 2 years, every consumer device will have hardware specifically designed for running AI models efficiently. Third, dynamic model routing. Instead of one model fits all, systems will automatically route queries to the right-sized model. Simple questions go to a tiny model running locally. Complex reasoning goes to a large model in the cloud. This happens transparently and keeps costs down while maintaining quality where it matters.
Brilliant. Here are the key takeaways. Quantization shrinks models 4 times with minimal quality loss. GGUF for CPU, GPTQ for quality, AWQ for production serving. Speculative decoding makes inference 2 to 3 times faster with zero quality loss. vLLM is the best starting point for production serving. Edge AI is real and coming fast, with phones running capable models locally within 2 years. And the deployment strategy is not either-or. Hybrid approaches that route queries to the right tier give you the best of all worlds. Check out our model optimization series, blogs 27 through 32 at AmticSoft, blogspot.com. Subscribe on YouTube, follow us on LinkedIn and X, and support us at buymecoffee.com/AmticSoft. That wraps up today's bot thoughts. Keep building, keep learning, and keep thinking. See you next time.